So in the half hour I have remaining, I'd like to talk about differential analysis of fluid flow. This chapter is mathematical. This chapter is less appealing to the majority of students than the previous chapter. Why? Because it requires a recall of calculus, differential equations, PDEs, vector differential and integral calculus, etc. So let's just get into it. We're going to have not just a conservation of mass statement. We've had that before, but it was an integral statement of the conservation of mass. We also had an integral statement of linear momentum balance, did we not? But now we're going to have a differential statement using differential equations. The Navier-Stokes equation, it's like if somebody graduates and they say, hey, you passed fluid mechanics. Do you know anything about the Bernoulli's equation? And they say, what? The Bernoulli who? That would be bad news, right? Just like pedo what? Pedo tube? Never heard of it. No, don't do that. Well, Navier-Stokes is one of those buzzwords. There's two people, they developed it. They developed the mathematical equation for differential equation for fluid flow. This equation is the Navier-Stokes equation. Okay? We'll bust it down and go slowly. What I'm going to do, instead of just deriving it, I'm going to show it to you and then talk about building up and reviewing the mathematics behind it. This is the conservation of mass equation, or the continuity equation. Just take a look at this equation for a minute. What does this lowercase t stand for? Time. So it's a time derivative. What is rho? Density. Sometimes we have incompressible substances. Rho is constant. A lot of times that term goes away. True? But this is a more general equation. You could have it where the density is changing as a function of time. Let's take a look. What is this V with the arrow on it? Velocity. And so it's our Eulerian description of fluid flow. Think about a grid, and every point in the grid has a velocity, and that's the chunks of fluid flowing over through that grid. What is that rho? Density. Sometimes you'll see this rho V together. This is a tough question. What is an interpretation, a physical interpretation of the product rho V? Yeah, but okay, it's like a mass flux. It's the if I said rho VA, oh, hey, that's the mass flow rate down a pipe, true? But if I took and divided by A and divided by A, I got rid of the A, what would I have? Well, mass flow rate through the area down the pipe. Or mass flow rate per unit area, mass flux. All right. What is this del right here? That's a mathematical operator. And so when you see del with the little arrow on it, think of the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk. True or false? Now, when you see that with this dot, what is that all called? Yeah. It's the gradient or the divergence, or might as well throw it out in the curl. Div, grad, curl. I mean, one of those three, right? The divergence, the gradient, or the curl. Okay, we're going to have a quiz, huh? Is that term right there, answer A. The divergence, the gradient, or the curl, or all of above. All right. So this is the del. That's what we call it, del. And then the del is, the gradient is del operating on something. The divergence is del dotted with something. And the curl is del crossed something. True? So let's take a look. We're in trouble. At least the D's were honest. I think I would say the D's, all of the above means I don't know. I have no idea. No, D's not right. What is right? Isn't it the divergence operator? Okay, we're going to keep on. Now, what does the divergence indicate? When it, it's like I do something, I have some input to the divergence, and what does it physically measure or report back? Whether the flow is either converging into or spreading. That's a measure of its spread, tendency for being spreading or concentrating. How about the gradient? It's how it's sloping. How I change the value as I change location. Is it going steep over here, shallow, not so? What about the curl? How the flow is rotating, going, swirling. All right. So this is the continuity equation. It's a conservation of mass. Often it's steady state. Often the density goes outside because it's constant. It boils down to just del dot V equal to 0 in a lot of cases. The divergence of the velocity field is 0. A lot of cases. Okay, well that was the easy one. Ready to move on? The Navier-Stokes. What is this big D doing there? Typo, right? No, what is it? Material derivative or substantial derivative or advective derivative, something like that. What's it measure? It's operating on V, the velocity, so it's measuring the material particle's acceleration at that point in the flow field. So I multiply by rho. This Navier-Stokes equation is a linear momentum equation. We already talked about F equal to ma is one way at Newton's second law. Isn't that a linear momentum equation? Or F is equal to mv. What does this term look like? Does it look like the F or the ma? It's the ma. It's the change in the linear momentum. Okay, then what does all of this look like or need to look like? Some of the forces, the things that go to change the linear momentum. Well, what is P? Pressure. And now I have a gradient of pressure. Go back to what does this gradient of pressure mean? Does it mean that I have pressures pretty well uniform everywhere around that point? That would mean a very small or 0 value for the gradient of the pressure. Or is it high pressure on one side of the point, low pressure on the other side of the point? Hence, it would want to push it for the pressure, be a net force. So that's the sense of this contribution right here. Pressure would be like a normal surface force around that point. How about this term? Rho g. The presence of gravity, and a little chunk of fluid has some density, has some mass, it would feel it. This equation will work if the fluid isn't moving at all, and it's just in good old fluid statics. Oh, please, let's go back to chapter, in fluid statics. Unfortunately, this course is not just fluid statics, it's fluid mechanics, which includes statics and dynamics. But this equation degrades down to just equation for fluid statics. All right. What about this term? Professor, I don't know. But what is del squared? Another name for del squared is Laplacian operator. That's exactly right. And so what is del squared defined as? The divergence of the gradient. What does it measure? Curvature, the second derivative, not the slope, but the second derivative. Well, what is this term trying to describe right here then? Well, it's probably easier to decipher by focusing on that parameter in front. What is that parameter? Mu is what? Viscosity. So not only can a fluid have normal force, pressure, it can have shear force due to some fast fluid chunks around it and slow fluid chunks around it. Hence, there's a shearing. The fast want to help it move fast. The slow want to help it move slow. So that is the viscous shear forces or stresses. So this is viscous. This is the gravity, and then this is the normal due to pressure. This is your material derivative, how it likes to be described as accelerating. Well, before we launch in and get, Laplacian, divergence, gradient, material derivative, we have to make sure our mathematical foundation is firm. So, dot product, go back and please review all about the dot product. The gradient operator, what's it take? What do you put into the gradient operator? Vector field or scalar field? What do you get out? Vector. Now you can put in notation a gradient of a vector field, but this is the traditional use. You can do it for a vector field. It would be done on each of the components. How about divergence? What do you usually put in here? Vector field. What do you get out? Scalar field. What about the curl? What do you typically put in? Vector field. What do you typically get out? Vector field. What about the Laplacian? Laplacian, what do you typically put in? Scalar. And what do you get out? Scalar. And then you need to have interpretations of each of these. I did that before, but instead of repeating them, I'll press forward. Can you write an equation that describes a two-dimensional scalar field? What would be described by a scalar field? Give me an example of something in fluid mechanics that we want to describe by a scalar field. That means at every point it has a value. Yes, it has units too, but it's not described by a vector at every point, but by a scalar. Pressure. So we say pressure, two-dimensional, x and y. Just make up a field. 5 plus 20x squared divided by the log of y. I didn't say it was a pretty one. I didn't say it had any meaning, but there it is. Now that you have a nice scalar field, could you calculate the gradient of that scalar field? This is yes or no. Then could you calculate the divergence of it? Yes or no. And could you calculate the curl? Yes or no. Well, first of all, let's say with the traditional use of divergence and gradient and curl. So for the gradient, yes, you should be able to do it. Divergence, divergence needs a vector field. How about the curl? Needs a vector field. Okay? But then once you say, yes, I can do it, then they say, prove it. So if you said the gradient of the pressure, it's the partial of the pressure with respect to x, partial pressure with respect to y. True or false? And now it's a partial derivative. Can you get those partial derivatives? Just make up an equation for a two-dimensional vector field. In fluid mechanics, what would we use a vector field to describe? Not pressure, but flow velocity. So V, it'll have to have some ui plus vj. Well, something like the cosine of x times y cubed plus 5 I can write I, plus something, some function, I don't know, we can make it up. Natural log of x times y divided by x squared j. There, I just made it up. Now, how about yes or no on the gradient of that vector field? No. But could we get yes or no the divergence of that vector field? You should be able to do that. And then yes or no the curl of that vector field? Yeah, we should be able to do that. All right. So how do you calculate the gradient of P? It's the partial of P with respect to x I plus the partial of P with respect to y j plus the partial of P with respect to z k. And so how many people did that as 2yz squared? I. 2xz squared j. 4xyzk. Did it work? It's really interesting that this tool is so easy to use and it's so readily available. And you would think, type in gradient of, and boom, look at that. Notice the notation. They use the curl with a comma, comma for the I, J, and the K component. And it's, hey, they had no tools like this when I was a student. How about the Laplacian? Well, you would calculate del squared of P. But am I going to have something I, something J, something K on the Laplacian? No. So it's just going to be the second derivative of pressure with respect to x, and the second derivative of pressure with respect to y, and the second derivative of pressure with respect to z. True? And you can even type in Laplacian of, and it's 4xy. 4xy for the answer. Pretty slick, huh? You could check yourself if you wanted to make your own homework problems. Wow, it only gets worse. Calculate the divergence of V. Is V a vector field described with U, V, W? Yeah. Where this is the U component in front of the I. This is the V component in front of J. This is the W component in front of K. Could we calculate the divergence of that? So is del dot the divergence of V? Is that the partial of U with respect to x plus the partial of V with respect to y plus the partial of W with respect to Z, and just add them together? Yeah, I think so. And then you just have a challenge to do those partial derivatives of each of those components. I encourage you to just refresh your memory. Oh boy. Calculate the gradient of the pressure in cylindrical coordinates. Instead of x, y, z for Cartesian, we have r, theta, z for cylindrical coordinates. Okay. Here's the pressure. There's r, there's z. Where's theta? Whew. No function of theta, which is simple function, right? But what is the gradient of P? Is it supposed to be giving back something E in the R, E in the theta, E in the Z? What are those little E's with hats on them? Unit coordinate vectors, exactly. That's right. And so is it something, our answer going to be something like this, the structure of it? All right, what do I put here generically before I try and apply it to this problem? Would this be the partial of P with respect to R? Makes sense. Would this be the partial of P with respect to theta? Would this be the partial of P with respect to Z? I have one error. I have one error. What's the error? What's the error? Yep, 1 over r, and we put it right there. True? All right, so once you know the formula, now it's pretty straightforward. What about the divergence of V in cylindrical coordinates? Well, boy, oh boy. This is my V sub r. This is my V sub theta. This is my B sub z. And those are my unit vectors, E sub r, E sub theta, E sub z. How do I calculate del dot V? Well, first of all, do I get back a scalar or do I get back a vector quantity? Yeah. Is it going to be, let me do this one. This del, is that equal to the partial with respect to r, e sub r, plus 1 over r partial with respect to theta, e sub theta, plus 1 over, the partial with respect to z, e sub z. Is that one way of describing the del operator in the cylindrical coordinates? Hence, what we would do is we would say, just put that formula down, the partial with respect to r, e sub r, plus 1 over r partial with respect to theta, e sub theta, plus 1 over, well, the partial with respect to z, e sub z, dotted with v sub r, e sub r, plus v sub theta, e sub theta, plus v sub z, e sub z. I think if you break it down that way, it's a lot easier, true? And so this comes to the partial of v sub r with respect to r plus 1 over r partial of v sub theta with respect to theta plus the partial with respect to z of v sub z. What does this equation look like? Yeah, the divergence theorem, right? So what is the beauty of the divergence theorem? That's exactly it. It converts a area integral over an enclosing surface to a volume integral over that volume that was enclosed by the area. Why do we have a little circle in the middle of this integral? It has to be an enclosing. Has to be an enclosing area. It can't be like half of it. You got to, it works for the whole. Hence, this is integrates over the complete volume that's there. Well, what is this G? It's a vector field, and you dot it with the outward directed normal vector. Then you make that area integral over the enclosing. But you can replace that with a volume integral where this del dot is the divergence of the vector field G. Now this is very mathematical, true, but it's like a lot of things in engineering. You either take the brute force, like never thought that the mathematician worked on the problem before, and I'll just go at it that way in my derivation of our continuity and Navier-Stokes equation. I would call that an engineer's approach to the derivation of the continuity and Navier-Stokes equations, which I'll do next time. Or you just say, we took so many hours of mathematics as students, learning from all the mathematicians, all these great theorems, why don't we use them every now and then? And then the derivation is about 3 steps. The derivation goes so fast that it makes your head spin. I got the derivation here. So you would say something like this. I will start with the integral statement of the conservation of mass. Reynolds transport theorem will allow me to start with the integral conservation statement for linear momentum. But for the conservation of mass, then I say, well, what's the mass in a control volume? That's easy. It's just a volume integral. This flux out, oh, look at that, V dotted N. That looks like I can apply divergence theorem. Now I have a volume integral and a volume integral. Combine those volume integrals into one volume integral. They have to be 0 regardless of where the little volume integral is applied to. Let it shrink to a point. The integrand, what's inside has to be 0. But there it is. That's the continuity equation.